Hey everybody, I'm Brett Eiffert of Oak Ridge National Lab, and along with my partner Josh Milthorpe and myself, under the support of Jeff Fetter, I'm going to present to you Scalable GPU sort on Frontier. Last year at CHU 2023, my project partner Josh Milthorpe presented something similar to this for Summit and NVIDIA systems. So in this iteration, we'll be showing the results on Frontier. Still using the Georgia Tech GPU API, which is developed by Agihiro Hayashi. I'll be showing performance on Frontier and the mixed results we got from that. And then finally, we'll show what we've done with Chapel GPU code generation and future ideas we have with it. For our GPU sort benchmarks, we're using Arcuda, and if you haven't heard of Arcuda, it's probably the number one, no, not probably, definitely the most, what do you call it, the number one Chapel application out there right now. So this year we're using Frontier. As you can see how it differs from Summit as far as the throughput in the CPU and the GPU range. Frontier is obviously a newer system, yet it only has half the CPU throughput of an older system, 4 years later, while you can tell Frontier has prioritized GPU throughput as, I believe it's 97%, if you do the math, 97% of throughput on Frontier is through the GPU. So here's how Arcuda is laid out. Again, I'm sure most of you probably already know this, but just in case, Arcuda uses a Python front end, and when you run the Python front end, it will send messages with the operations to the backend Chapel server, which does the heavy lifting for whatever operations it sends, such as sort. And this is kind of where this Chapel backend server is where we've fit in our there it is fit in our GPU API code to push out things to the GPU. I've been referencing the Georgia Tech GPU API, but what is it? So the Georgia Tech GPU API is used to abstract over GPU programming models. So in our case, recently it was CUDA, now it's HIP. So there's kind of two parts to this. There's the GPU iterator, which allows you to launch kernels, so CUDA kernels, HIP kernels, directly from Chapel. And then so that's kind of a low level, and then there's the GPU API, which is a little bit higher level, which allows you to manage memory, manage arrays, transfer data through more of a user-friendly interface, and also around it also provides wrappers around device functions. In addition to the standard GPU API out-of-the-box host GPU transfer, we added the capability of shared virtual or unified memory through the GPU unified disk class. Shared virtual memory, or unified memory, is where the host and devices share pointers to a single unified memory space. Any reference to memory not in the right place when accessed will result in a page fault, which is then handled by the code. Later on, I'll talk more about this. Below is an example code of the basics of how unified memory array is allocated through the GPU unified disk class. And on the bottom right, my partner Josh made a nice diagram to show the simplicity yet effectiveness of this unified memory concept. Here's GPU unified disk in action. This example uses sum. All other examples and explorations in this presentation are with sort, but sum is a little bit more simple to show. So that's what we'll use. The first line, launch sum, uses the GPU iterator, and use that to launch out to GPU kernels. Then cub_sum illustrates the GPU API, so stepping through the important parts of the code. Dev out, you can allocate a new GPU array based on one of the devices and the device ID. And then we can do a prefetch before we actually launch the kernel. The prefetch allows you to launch the kernel without all the data loaded onto the device. And that can, in theory, allow operations to perform faster because you're no longer waiting for all the data to transfer at once before you start any operation. And then at the end you synchronize the devices and then you transfer the data out of the device. Finally, getting to Frontier. Here are the system specs of a single node on Frontier. On Frontier we ran our sorts using the Arcuda radix sort LSD, least significant digit. And it's important to note that we did not use the full Arcuda client server interaction. We just used the Arcuda Chapel code directly. This is a Frontier compute node schema. As you can see, it's no secret that if you look at the key, it's no secret that Frontier is optimized for GPUs. You can see the out-of-network NICs are connected directly to the GPUs. The NUMA domains are connected to a specific GPU device, as in NUMA 3 is connected to GPU 0 and 1. And yeah, if you kind of look at the schema, you kind of start to figure out, like, okay, these are the things we need to optimize our code for. Here's a single node benchmark on Frontier of sort. The 4 runs we did were 1, the Arcuda CPU implementation of the radix sort LSD, a GPU cub sort with a CPU merge, a GPU cub sort with a GPU merge, and then the default Chapel sort. And as you can see, as the sample size got big enough, close to 1 billion elements, the GPU cub sort with the GPU merge finally passed the CPU. As mentioned in the previous slide, the GPU peer-to-peer merge beats the Arcuda CPU for large data at 1 billion elements. And as you'd expect, 60% of the time in these GPU sorts is data transfer to and from GPUs. And actually we found out, and I'll go into it later, that Chapel is not using the GPU high bandwidth memory within Frontier as we would like it. So we started to explore these long data transfer times. And, this is GPUs. There's always going to be, a lot of time spent data transferring. We just think it's higher than it should be. In the top right, it shows 1 through 16 nodes and how long it takes to merge and how long it takes to run the GPU sort kernel. And again, yeah, it's always going to be more time merging, but we think that this it's spending too long merging and swapping. On the bottom right, the most important part of that bar graph is the far right, which is the disk merge, especially as it goes from 8 nodes in the yellow to 16 nodes in the blue. It does a large jump, and instead of, you would hope, would be that the bar graphs would be pretty similar, but it's increasing all the way and then a big jump into 16 nodes. And actually we stopped at 16 nodes because 32 nodes was pretty much breaking our sort. In investigating these slow data transfer times, we came up with a list of important limitations that we observed. So Frontier communicates between nodes through the GPU. When we're transferring data, we actually have seen the data going through the host and then back to the GPU before it actually transfers out, so that's a significant slowdown. There's also repeated communications in the same session becoming slower. There's also a lack of NUMA awareness of GPU arrays actually in Chapel. I guess it doesn't have that level of granularity right now. And then also this prefetch operation I had talked about earlier doesn't seem to improve the kernel time. I'm assuming that's a AMD or ROCm issue. I'm not sure if it's actually implemented or not, but that's interesting. We set up a internode communications ping pong benchmark on Frontier to test different configurations to see where the bottlenecks are or what works and what doesn't. So of the 6 options here, the best performing bandwidth was GPU-aware MPI, and this makes sense because Frontier is connected to other nodes through the GPU. The next highest was just Chapel standard host, no GPU, Malik, but still significantly slower than the GPU-aware MPI. And then again, it would make sense that the non-GPU-aware MPI would be even lower. And then all the way at the bottom is where our, those 3 is where our current runs are right now in our benchmarks, which is almost, 10, 15, maybe 20 times slower than where we should be at Frontier, which is that gray line. So that's really interesting, and that's one of the limitations we've seen with Chapel and Chapel GPU API on Frontier. As mentioned before, the way nodes communicate is actually through the GPUs, as seen highlighted here in this diagram. Chapel OFI comms layer doesn't utilize libfabric FIHMEM, internode device support. There's no way to reach this memory directly, and you would need to register device memory regions, which could require a new memory allocator. So sadly, Chapel distributed arrays aren't NUMA aware. Mentioned earlier, now I'm mentioning here that Frontier has these NUMA domains that are linked specifically to each compute die, to each GPU and compute die. And to fully optimize our code for this, we would need to have NUMA-aware placement of host array segments. And right now, we don't have that. We're trying Chapel and Chapel GPU API on Frontier. We decided to move on to Chapel GPU code generation and the codability of it. These 2 functions currently do not accept GPU arrays as target locales. They just take locales. But it'd be nice to be able to pass in an array of GPUs and as a drop-in replacement, and it would still work. This would help when the codability of Chapel with GPUs as far as managing swaps and pivots and merges. Another example with swaps, how fairly nice this is to work with, but just it's not right now usable with GPUs, and in the future it would be great that if GPUs could use this function almost directly. So the purpose of this slide is just to show the complexity of a sort and the swapping and merging portion of the sort. Just as far as, I guess the algorithm is fairly simple, but when you're actually accessing the data and accessing the array slices, it gets complicated as far as, okay, you're taking a GPU on node 1 and another GPU on node 1 and swapping. You have to get those pointers manually through the current GPU API implementation. Also, even more difficult is getting a GPU pointer from one node and then swapping it with another GPU pointer on a different node. And this is kind of just illustrating that, and later we'll talk about, and show the code of how this is complicated and how we can improve it. This is the type of code we call when we want to find the pivot in the swap and merge algorithm, usually called, which is usually part of a sort. Obviously, this is not ideal just to call this every time you need to find a pivot when doing swap and merging in a sort, and that's why we want GPU codegen to fix this problem. Same with swap in this algorithm. have to call nasty GPU kernels just to swap between two values between GPUs. And again, this is not ideal when developing a large sort algorithm. The merge portion of the sort is not bad. Um, this is acceptable code versus the other two previous slides that were. I'm writing this. I feel as a developer using, hopefully, using Chapel GPU CodeGen. This is something I find acceptable when developing. So this portion of the merge and swap algorithm um, is fine. This slide to kind of summarize my thoughts of the previous few slides. So as seen on those slides, there were some portions of code that were just not very readable or writable. And ideally, Chapel GPU CodeGen can use existing, or at least the functionality and the way you write it is kind of the same as it already is with CPUs. So like when you're allocating a distributed GPU array across all GPUs on a node, you could just write it like you already would with CPUs, except you would just give it a GPU array instead of a list of nodes. So same with copying between between two devices on a single node, and then also same with copying between two devices on different nodes. This kind of code looks very nice, and it is not nice currently with GPUs, and this is kind of what we're hoping to see in the future of Chapel GPU CodeGen. In our work on Frontier, we used the Georgia Tech GPU API, which was granular, but was also met with limitations and some tedious and difficult to debug code. We also encountered Frontier and AMD specific issues like ROCm bugs. We also saw that Frontier and Chapel were incompatible in some ways, like how Frontier is optimized to the GPUs on memory transfers, and Chapel is not aware of that. And also Chapel is not aware, or Chapel's arrays are not NUMA aware. So we weren't able to optimize in that way. And then we're also able to explore Chapel GPU CodeGen and how that could potentially solve our problems in the future. We've tried Chapel GPU CodeGen some. We realize it's a work in progress. And yeah, we were just hoping to give feedback on that and give potential solutions for when things are solved in the future. All right, thanks for listening, guys. I'm willing to take, I guess if we have time, I'm willing to take a question.
Do we have any questions?
I can ask a question. So first of all, this is really valuable information, Brett, and particularly I think the lack of integration with the network layer between the GPU is really telling and not surprising to me in the sense that I don't think we've really done much to sort of try to integrate GPUs in the memory layer beyond sort of what just naturally falls out from Chapel. Also, your point about the NUMA awareness is a little bit surprising. Like, we definitely work hard to try to be heuristically NUMA aware with our distributed arrays, but certainly the better thing there would be the colocale support, which, as we were talking about in one of the earlier talks, isn't really integrated well with GPUs yet. So that feels like a potential valuable thing coming up, but isn't quite there yet. But my question for you was, you've listed kind of a number of areas where we could be doing more or falling short relative to kind of conventional lower level technologies. Do you have a sense from a prioritization perspective of if, let's say we could just do one thing next, what would give the most bang for the buck? What would kind of turn these results around the most based on your experience?
Yeah, I mean, I don't know. I guess I don't know if this is selfish or not, but it's just like, okay, we have this shiny new supercomputer Frontier, and we're not unable to use that high bandwidth memory. I think I don't know if other systems are going to be designed like that, or there are. I don't really know if I don't know if there are other systems that are designed like that, but I think that would be probably the most valuable. I don't know if you have a different opinion, Josh.
Yeah, I think for the Frontier results is definitely the libfabric support for attached accelerator devices, like that would make a huge difference for systems like Frontier, where the network interface cards are directly attached to the accelerators. Yeah, we could probably get good scalability out of this on many nodes of Frontier if that were fixed.
Okay, great. I really appreciate that. Thanks very much.
There are two more questions in the chat, but as we're entering the break time, Brad, would you mind kind of answering them in the chat or during the break? And then I guess
Sure.
we'll see everyone back for the keynote talk in 15 minutes.
You can take a look at Tess's question first, which is sort of similar.
Yeah, so Tess, I'll read this one out, Brett. Tess
Yeah,
asks,
sorry, I couldn't. Yeah, sorry, I couldn't see it.
Yeah, Tess asks, is the NUMA-aware issue solved by colocales? And if so, have we had a chance to look into this since it was added? Yeah, Tess, I think this is probably the best current solution for the NUMA awareness. So yeah, we would divide Frontier up into 4 colocales, each one NUMA domain with 2 attached GPUs. Yeah, I think that would solve the NUMA host memory issue. I guess the downside there was now the colocales, if I understand correctly, don't recognize that the GPUs and the other colocales are attached, in any particular way. So I still think we have the same kind of issues of transferring between GPU devices between different colocales on the same node. But yeah, that's something that we should try.
Hey, Brett, I had this question for your slide 23, as I put in chat, where you had this like list of items that was sort of like a wish list, like I wish this was working with the GPU code generation. So among those, the top one definitely doesn't work today. And I think you and I had a chat about this. That's about distributed arrays and being, memory allocated on the GPU. The other 2, I don't remember the details of those, but they strike me as like they should work today. I agree that they're kind of complicated, but like if you bumped into issues running those kind of idioms, the bottom 2, we should take a look. Like I would qualify them as bugs rather than unimplemented things if they are not working today. As I said, definitely more complicated than tests that we are doing today, but fundamentally they look the same. But
Okay, thanks.
Yeah, but maybe there was a lot on that slide, but I think, Engin, the both of those bottom 2 examples assume that the array A is distributed first across multiple devices on a node, and then the second one distributed across multiple devices on multiple nodes.
Okay.
So yeah, like they kind of relied on the first wish list thing. Yeah.
That definitely clarifies it. Okay, yeah, then yeah, they won't work. Yeah, I agree with that. And it's definitely near our, priority list to support the distributed arrays, which is big lift. We made some progress, but the progress that we made is probably not very visible to the end user just now, like just wiring things appropriately in the compiler and the runtime, so that we can build up support for it. But yeah, it could be really powerful if you can use distributed arrays with GPUs. I definitely agree.